Let's take an introductory look at the airplane, its controls, and the aerodynamics that make it fly.
The four forces which act on an airplane in flight are lift, weight, thrust, and drag. Lift is the force that acts upward against weight, which is caused by gravity. Thrust propels the airplane forward, and drag acts opposite of thrust.
Let's begin with lift and take a brief look at how lift is produced and how the airplane is controlled by the pilot. Because an airplane is heavier than air, the wings must do something to the surrounding air to make the air support the weight of the airplane.
A Swiss mathematician, Daniel Bernoulli, found that if the speed or velocity of a fluid or gas is increased, there will be a decrease in pressure at the point of the increase in speed. Looking at the cross-section of the wing, we can see that the upper surface is curved and the lower surface is relatively flat. As airflow meets the wing, the air flowing over the top curve, or camber, is speeded up, decreasing the pressure on the top of the wing. This decreased pressure is the major source of the lift needed to make the airplane fly. However, we must also consider the effect of the air striking the bottom of the wing and being deflected downward. As the wing pushes down on the air exerts an equal and opposite force on the wing. The increased pressure on the bottom of the wing also creates lift. While the decrease in pressure on top of the wing is the greater source of lift, the lift made by increased pressure at the bottom of the wing is important when we look at the total lift needed to fly the airplane. The increased pressure below the wing is a working model of the concept of action-reaction, which is credited to Sir Isaac Newton. Interestingly, the discoveries made by Bernoulli and Newton in the late 17th and early 18th centuries are the basis for heavier-than-air flight, but they weren't seriously explored until the 1900s. Before we leave airfoils, let's name the principal parts of an airfoil. The front is called the leading edge, and the back is called the trailing edge. In cross-section, an imaginary line drawn between the leading edge and the trailing edge is called the wing chord. Later, we'll see that the relationship between the wing chord and airflow is important when we control lift. The top curve is called the upper camber, and the bottom curve of the wing is the lower camber. In the next video volume, we'll continue with an in-depth look at all the forces involved in flight. An airplane in flight is free to rotate around 3 axes, which pass through the airplane's center of gravity. The axis which passes through the length of the airplane is the longitudinal, or long axis. Movement around this axis is called roll, or bank. The axis which passes through the fuselage at a right angle is the lateral axis, and movement around this axis is pitch. The remaining axis, which passes down through the fuselage at a right angle to both the longitudinal and lateral axes, is the vertical axis. Yaw is the movement around the vertical axis. To maneuver an airplane, you must control its movement around these 3 axes. This is done by moving the primary control surfaces, the elevator, ailerons, and rudder, from the neutral position into the airflow.
Let's look at each of the primary control surfaces, how they work in flight, and the inputs we use to move them.
Ailerons, the control surfaces at the outboard ends of the wings, control roll. Pitch is controlled by the elevator, and the rudder controls yaw. The horizontal and vertical stabilizers act like the feathers on the tail of an arrow to balance the wing and help keep the aircraft on a straight course. Pulling the yoke back moves the elevator to rotate the airplane around the lateral axis, pitching the nose up. Conversely, pushing the yoke forward will move the elevator, pitching the nose down. But if you've seen an airplane upside down, you'll realize the pilot of the inverted airplane has to think in terms of the nose moving toward or away from him, not up or down. Turning the control yoke moves the ailerons, and moving the yoke fore and aft controls the elevator. This allows either the elevator or the ailerons to be moved individually or simultaneously. I want to pause right here and tell you the control movements we're using here are exaggerated for illustration purposes. When you're flying, the movements are more subtle. Turning the yoke to the right will move the right aileron up, while the left aileron moves down. Air flowing over the deflected ailerons will make the airplane roll around the longitudinal axis and bank to the right. When the yoke is turned to the left aileron is up and the right aileron is down, making the airplane bank to the left. The bank will continue to increase until the ailerons are returned to the neutral position. When the ailerons are in the neutral position, the aircraft tends to stay in the bank until the yoke is turned opposite the bank to make the ailerons roll the airplane back to a wings level position. Pushing the right rudder pedal moves the rudder to the right, causing the airflow to move the tail to the left, which yaws the nose to the right. Remember, yawing the nose is not necessarily turning the airplane. Pushing on the left rudder pedal will yaw the nose to the left.
Why does an airplane have a rudder if it doesn't turn the airplane? Well, let's take another look at what happens when the ailerons are deflected into the airflow.
The deflected ailerons change the wing chord of the outboard part of the wings, which in turn changes the lift of the wings. Also, the down aileron is in higher pressure while the up aileron is in lower pressure. The drag or retarding force is greater on the wing with the down aileron, causing the airplane to yaw to the opposite side of the bank. This tendency to yaw opposite the bank is called adverse yaw.
In turning flight, the rudder's only function is to counteract the adverse yaw, which happens when the airplane is rolled into a turn and when it's rolled back to wings level flight.
A trim tab is used to relieve the pressure or force needed to hold a primary control surface out of the streamlined position. Trim tabs are attached to the trailing edge of the primary control surface. The elevator trim tab is moved opposite the position of the elevator to reduce the pressure the pilot must use to hold the elevator into the airflow. The position of the elevator determines the speed of the airplane, and the elevator trim is used to maintain a constant speed, not a constant pitch. Elevator trim can be adjusted in flight, but on most training aircraft, rudder trim can only be adjusted on the ground. The flaps are the panels on the trailing edge of the inboard parts of the wings. Unlike ailerons, both flaps are extended and retracted at the same time. Lowering the flaps changes the chord of the wing and increases both lift and drag. Extending the flaps allows the landing approach to be steeper and slower. In some situations, flaps are also used to shorten the takeoff run.
This completes our first look at the airplane and the natural forces acting on it in flight. To be a safe and efficient pilot, you must first understand the principles involved and learn to either utilize or counteract these natural forces.